like that. You know, a light like one bikers, it goes in the full circle. That's what I'm saying. So I said, because what are you talking about?
All right. So think about, see that's attached to that spoke right there. So if I have my finger on the tire, as it moves, my finger lifts upwards. Now the normal force is acting on that spot only while it's in contact. So as soon as it rolls, it's not in contact anymore. And friction is acting this way up the ramp. But that point right there is moving this way. They're perpendicular to each other. So work only happens if there's some parallel or anti-parallel component. Therefore, as it's rolling down, this is the only thing doing work. Therefore, it's conservative force. Since it's conservative force, energy is conserved. So the energy at the top equals the energy at the bottom. What are the two types of energy that we care about here?
Why did we conclude that weight is still only conservative force?
Why did we, say it again?
Like, why did we not consider the normal and friction force?
The normal friction, or sorry, the normal force, if you recall, work is force times displacement. I have some normal force acting that way. But the displacement, this normal force is acting on that plane of contact.
Yeah.
The displacement is infinitesimally small. Because as it rolls, that point is only in contact with the surface very briefly, and then it lifts up. So as soon as that, so if I zoom in on that spot, and I have that point in contact, as it rolls, that point will very quickly be right above it, and the normal force is no longer acting on it. So that's why the normal force is not doing any work.
But the displacement, what direction is it?
The displacement's in that direction. So initially, as soon as we have a normal force in the direction of displacement, but this number is so incredibly tiny, work is close enough to zero.
Okay.
Friction, acting this way, displacement is that way. They're perpendicular to each other, and the dot product of perpendicular vectors is zero. Yeah.
Thank you.
The two types of energy?
Conservative and non-conservative.
Those are types of work.
Kinetic.
Oh, kinetic.
And static.
Kinetic and potential energy.
Kinetic and potential.
I was close.
So I have kinetic energy plus potential energy. Initial is equal to the final values. Initial kinetic. What's the formula for kinetic energy?
1/2 mv squared.
All of you should say that. Don't worry, fill the other chances. Plus my potential energy. What's the formula for potential energy?
mgh. Well, we already know it.
Let's go through the exercise.
Oh man.
Which one?
The one associated with weight.
mgh.
There we go. Equals 1/2 mvi squared plus mgh final. Now we do have one other issue here though. It's the fact that this thing is rotating. And that's what part of what we went through before is the fact that not only is it moving down the ramp, but it is rotating and there's a rotational kinetic energy. So we do actually have two kinetic energies here. 1/2 I omega squared initial, and then over here 1/2 I omega final squared. Because we have two types of motion, we need to account for both of them.
Wait, why did we add those?
Because it's rolling as it's going down the ramp. And not everything on this mass here is moving at the same speed.
Right.
So we have to take that into account. can we get rid of anything? Let's assume it starts at rest.
0. The initial speed is 0.
And angular speed also.
We can define final height as 0.
Okay. So that's 0, because Robin said so. And we're left with a much simpler problem.
What did you write over there?
This,
Yeah.
BRSS, because Robin said so.
Oh.
He established final height to be 0 at the bottom. So I'm left with my potential energy at the top is equal to my kinetic energy at the bottom. All right, this thing is rolling. Let's stick in let's assume it's a ball, a solid sphere. So I is 2/5 mr squared. So I get mgh initial equals 1/2 mv final squared plus 1/2 times 2/5 mr squared omega final squared. And again, this is true if it's a solid sphere. Let's simplify. I got 1/2 times 2/5.
Wait, is the 1/2 mv squared at the top supposed to be an I?
There?
Yeah.
No, it's final. That's supposed to be an F right there.
No way. No shot. That straight line was supposed to be an F.
Who knows what I was thinking when they did that? There's no dot over it, but
There was no horizontal line either.
It's just subtle. You just don't understand.
Right.
So
Clearly.
Yeah. Sorry about that.
So we had to put the 1/2 mv squared and the 1/2 iw squared because it's moving. So there's kinetic energy, and since it's a ball rolling, there's also rotational motion.
Yes.
Okay.
Is that a...
There's an intermediate step that I have skipped here that I will eventually get to.
Okay.
Are all of the M's the same?
Yes, they are. So, you want to get rid of them?
Sure.
Okay. So let's go ahead and, I'll write down the next step. So that'd be 1/5 mr squared omega final squared. So think of once the mass is gone, every term has a mass as a factor, so we're good there. Now we've got this r omega. What's equal to r omega?
B.
Yes. So this becomes GH initial is equal to 1/2 V final squared plus 1/5 V final squared, which is 7/10 V final squared. Notice the mass was canceled out and the radius got absorbed into the speed. So R is gone. Doesn't matter what the radius is, R times omega, assuming that there's no slipping. If this is a perfect roll, this is legitimate. And so I'm left with GH initial is equal to 7/10 V final squared, basically simplifying the writing of that. And so my final speed is equal to the square root of 10 GHI over 7. If there were no rolling, this would be 2 GHI over 1. But rolling takes away some of the energy that goes into moving it down. Questions here? All right. So, looking at this slightly differently. If we start out with all this potential energy up here, as it moves down the ramp, there's two things that energy goes into. That potential energy gets transformed to kinetic energy. Part of that kinetic energy is getting it to roll. Part of the kinetic energy is getting the thing to move down the ramp. The higher that fraction is up front, the higher this number here is, the more energy goes into the rolling, which means there's less left over for the energy to go into things to move down the ramp. So this has a lower fraction than this does. This is 1/2, this is 2/5. So this will require more energy to getting it to roll and has less left over to get it to move down the ramp. This one, less energy to roll, more energy left over to move it down the ramp. This will be faster.
More energy left?
Yeah, if I have a certain amount of energy, I have a certain amount of potential energy that I will distribute into getting the object to roll and getting it to move down the ramp. The more I spend on getting it to roll, the less money is left over, or less energy is left over to get it to move down the ramp.
But because it's less, that's going to be more.
Yes. Questions here? Now, if I have this and I'm rotating it about the center, I have my moment of inertia of 1/2 mr squared. Suppose instead I want to rotate it about an axis on the side. Would that increase moment of inertia or decrease it? So the equivalent would be I'm spinning this disk about an axis like that, or spinning it about an axis like that. Which one's easier to do?
I don't even understand what you're...
If I have an object that I'm rotating about some axis, I'm going to take this and I'm rotating it about an axis going straight down.
Okay.
Now, instead of rotating, it has a certain moment of inertia, that also happens to be 1/2 mr squared. If instead of rotating about an axis there, I want to rotate about an axis here.
Right.
So this is now fixed, and I'm rotating the wheel around that spot, around that axis of rotation. Which one has a greater moment of inertia?
Wouldn't they be the same? Wouldn't they be the same?
They would not.
I say that one would be more moment of inertia.
Around like this, or you said that
The
one?
second one. That one.
That one? Why?
I'm just imagining myself doing it in like a heavy boulder.
Uh-huh.
And I just thought like pushing it across an axis would be a lot harder than just like rotating around itself.
Okay.
I think the first one's
Seems easier? Okay, so you two are in agreement. Because I think he said the other one, the second one was harder. You just said the first one was easier. Unless I misheard. That is correct. If you go back to just the formula, remember moment of inertia is the sum of all the MI/RI squared. In the first case, the farthest any mass is from the center is the radius. If I'm spinning about an axis right there that's going through the center, the farthest anything away is the radius. But if I'm spinning about an axis here, the farthest any mass is away is the diameter. It's twice as far. So I have more mass farther away from the axis, so the moment of inertia goes up. But if you look up in the textbook under the table of moments of inertia, it's probably not there. So I introduced to you the parallel axis theorem. And I know you're going to be disappointed by what I say next, but I'm not going to derive it. I don't like doing that, but
Aw, bummer.
yeah, it is. So if I have some shape with a moment of inertia, and there's its center of mass, so I'll mark the center of mass by a C. So if I'm rotating about an axis that's right there, so rotating about like that, it has some moment of inertia, which I'll label I sub C. It's the moment of inertia about the center of mass. If instead I rotate it about some point P, so basically I'm moving the axis to the edge here, then the moment of inertia about point P is going to be the moment of inertia about point C plus mh squared, where h is the distance that I moved the axis.
What is m again?
M is the mass of the object.
And then h is the distance between the c and the p?
Yes. How far did you move the axis? It is a parallel axis because the axis was here, perpendicular to the board, and now the axis is here, perpendicular to the board. So if I take the wheel, let's make it a solid disk. So if I take a solid disk, rotating about the center, I know the moment of inertia is 1/2 mr squared. If I move that axis out to here, so my first example was bad. So instead of rotating about like this, I'm rotating about that. That's about the center. So that's C and P. The moment of inertia about point P is going to be the moment of inertia, let's do it step by step, IC plus mr squared. Because I move the axis, the radius. So that's equal to I 1/2 mr squared plus mr squared gives me 3/2 mr squared. So by moving the axis, in this particular case, the radius, I've tripled the moment of inertia. It'd be 3 times harder to get it moving, 3 times harder to stop it. So if I have an object that is rolling, I have a point of contact right there. So let's say it's on a ramp. That's the point of contact. It's as if I have this object rotating about this point right here. Now that point is constantly changing, but in this, we take a snapshot, it's rotating about that point right there. So my kinetic energy is 1/2 I, call that point P omega squared. However fast it's rolling about that point right there. Using the parallel axis theorem, I get 1/2, that would be IC plus mh squared omega squared. Which is 1/2 IC omega squared plus 1/2 mh squared omega squared, distributing. That is the rotational kinetic energy about the center of mass. And this, well, h is, all I did was move the axis of rotation, the radius of it. So this piece right here becomes 1/2 mv squared, because that's r squared omega squared. And that's the kinetic energy of the center of mass moving down the ramp. So what we did in that previous example there is I just went ahead and jumped straight to this. But really, this is our formula for kinetic energy, and it happens to break down into the kinetic energy rotating about actual point of contact is just the moment of a rotational kinetic energy rotating about the center plus the kinetic energy of the center going down the ramp. The linear and the rotational kinetic. And that was the intermediate step that I actually skipped before.
So that theorem and the 1/2 I W squared plus 1/2 mv squared is true for any type of ball rolling across any ground, plane, or anything like that.
Assuming no slipping.
Okay.
If there is slipping involved, then suddenly we're dealing with a loss of kinetic energy, a loss of energy, and it's more complicated. We will not get beyond the ideal roll for any rolling. Questions here? Ritika?
Could we have used the 3/2 MR squared for the IP? Like, could we just have substituted that?
Ask that again, please.
Could we use the 3/2 MR squared in place of IP for kinetic energy?
The 3/2 is specific to a solid disk rolling, and
Is that a solid disk?
the second example is just something rolling.